Welcome to the lecture switch capacitor basics, and before starting this I would like to know whether do you have any idea about that switching circuit, anything about? Okay, now now this is one simple circuit, and this side we have voltage V1 and this side we have voltage V2. In between we have connected one resistance R. Now we are assuming that V1 is greater than V2, and these two are time varying signal. This is a function of t, function of t. Now if V1 is greater than V2, then for that case current I is equal to V1t minus V2t by R. Now this is the equation for the current. Now when we design circuits in VLSI, for that case we have some problem for implementing resistance into the chip, because in that case when we need some higher resistance, for that cases we need a very large area for that case. So at the same time when we fabricate high resistance into the chip, that time that accuracy also that is not very good. So some problems are there for implementing resistor, high value resistor into the chip. So that is why we have new design to replace this R using switch capacitor technique. Now how can we replace this R using capacitor? Now we are designing one equivalent circuit for this one. Now phi 1 and phi 2, these two are two different voltage pulse, and these two are used to operate these two switches. This is S1 and this is S2. So this is phi 1 and this is phi 2. Phi 1 and phi 2, these two are non-overlapping clock pulse. So what is happening when this is high, means for the digital circuit this is equal to 1.8 volt, this one for CMOS 9, this one 0 to this one. Now this is also 1.8 volt. Now when phi 1 is on for this one, that time this switch is on. So using this path this capacitor will be charged. After that when phi 1 is off and phi 2 is on, then the charge that was stored due to this process, the previous process, it will be transferred to this side. Now let's see what is happening here. For the first time when this switch phi 1 is on, for this one, for switch S1 is on using this phi 1 clock pulse, that time we have I is equal to 1 by T, 0 to T, I average this one, this side we are taking I1T and this side we are taking I2t. Now I1t dt. Now as this switch is on for this time, this much time period, for this one, this is t by 2 for example, but generally we take slight less than t by 2 because there will be rising time and fall time for this pulse. So actually these pulses are like this. So it is not like directly it is when one pulse stops the other pulse ends. It's not like this one. I mean it's not like when the first one ends the next one starts. It's not like this. In between we have the fall time and for this one the rise time, and we have as we have I have said that these two are non-overlapping clock pulse, so this should be a slight less than t by 2, but for the calculation we are taking this one as t by 2. So this is 0 to t by 2, then I1t dt. Now this I1t, this one, when this switch is on, that time it will be charged, this capacitor. So how much charge will be stored in this capacitor? That is equal to Q1 is equal to C into V1 for this one at this moment, at the same time here, and we can write that I T is equal to dQ1 dt. So if we are replacing this I1 by that dQ1 dt 0 to t by 2, then I average is equal to 1 by t 0 to t by 2 dQ1 is equal to 1 by t q1 t by t minus q1 0. Now let's see the first slide. Here q1 t by 2, this one, this voltage is equal to this one at this moment. This is equal to t by 2, this point. Now at this point phi 1 was on, after that it stopped, and till now phi 2 has not been started. So till this period this C is charged with this voltage, V1 voltage. So for that reason we can write that Q1 t by 2 is equal to, this is C into V1 t by 2 minus, for this one, this Q1 0 for 6. See this slide. Now as I have told that this is not exactly this phi 1 clock, this one they should not start exactly from 0 because there should be a gap in between. As I have told that these two are non-overlapping clock pulse, so it will start just after that 0th time level. So before that we had, here we had phi 2 clock pulse this side at the negative side. So for that reason now phi 2 was on, and after that just it has been stopped, and till now phi 1 has not been on, this one. So that is why now at this moment, now this capacitor was charged, with the previous value of phi 2 for this one. So that is equal to V2. So is equal to V2 0, V1 t by 2 minus C, sorry not C, I have taken common, Now suppose this side we have given one sample like this. This side, this is the SIMS, this is the sample. Now the time period, the frequency of this clocks, this is so high that we are considering for small time interval that V1 does not change. At the same time, V2 also does not change for that duration, for that T. This is equal to T. So this is equal to this voltage. We are considering that during this process, this V2 voltage at the same time V1 voltage, they are constant for that duration. So we are considering that V1 0 is equal to V1 T by 2 is equal to V1 T is equal to V1, and V2 0 V2 is it clear, this one? So for that instant we are considering that from 0th time to that, during that period, from that T time interval, that voltage is equal to constant V1, this one, this is equal to V1 and this is equal to V2. So here we can write I average is equal to C by T, C V1 minus C V2, sorry, let's take V1 minus V2. Can I write this one? This was the first slide, this one. Second slide, sorry, this is slide 1, 2. I average is equal to C by T V1 minus V2. Now we can write like this way, that I average is equal to V1 minus V2 by T by C, and this T is that time period of this clock pulse, this one, of this clock, this is equal to T, this one. So 1 by T is that clock frequency, and C is that capacitor. Now I average is equal to this one. Now this is equivalent to V1 minus V2 by R in the first circuit, this one, this one. Now comparing these two equations, we can write that R is equal to 1 by CF here. Now here we can see that we can have capacitor at the same time frequency also. Now it's very, compared to that resistor, to implement capacitor into the chip, that is much more easier. And to get a high resistance, we do not need any high resistance value, because if we if we decrease that frequency, then we can have large value of R. At the same time, if we increase the frequency, that time we can have small value of R. At the same time, we can say that if we keep this frequency constant, just changing the value of the capacitor also, we can have a different value of R what we need. Now this is the basic concept of that switching capacitor circuits, this one. Now let me tell in between, do you have any idea about these switches? How do you implement these switches? MOS capacitor circuit, sorry, MOS circuit, but now this is S1, this is S2. Now this is the way we design these switches is phi 1 is applied here, phi 2 is applied here. But we have to check whether these two are in triad region or not, because the MOS characteristics curve is like this. This side is VDS, this side is ID. ID and this is VDS. Now when we design switches, now we assume that there should be very less voltage drop across this switch. So VDS should be as less as possible, I mean as small as possible. So for that case, these are two different region to operate MOS. This is VGS minus VTH. Now beyond this, this is saturation region, and this side, this is triad region. Now these MOS switches are operated within this triad region, so that we can have very less VDS here, this side. So you have to check whether these switches are operated within triad region or not. Now when we are applying these pulses here, for example this is phi 1. Now in the previous slide I have written here that this is the in digital circuit this is equal to voltage 1 level. 1 level means that is equal to 1.8 for CMOS time, for example. I mean this is the maximum maximum voltage what you can have for that technology. So this is the maximum voltage. For example, this is 1.8 volt. Now if you are applying 1.8 volt, so in that case you cannot apply more than 1.8 volt this side or this side. This is not possible. So for any case, if you are applying the maximum potential here, so it will be in triad region. Is it clear? This one. Now here this is ID, this is for example this is the NMOS, VDS. Now here I have applied phi 1 pulse. Either it will be 1.8 or 0. Now 1.8 is the maximum voltage. Now if it is within that triad region, the condition is that VDS that should be less than VGS minus V threshold. So VGS should be greater than VDS plus VTH Now you are applying here maximum potential. Sorry. Now I can write Vg plus Vs is greater than Vd plus Vs plus Vth. I can cancel these two. It's not. So Vg should be greater than Vd plus Vth. Now Vd plus Vth, this one, this should be, I mean Vg should be greater than these two. Now see this one, if this is 1.8 volt and this is also maximum 1.8 volt, for example we are taking this one, so for that case, and at the same time we take, let's take two different cases. This is 1.8, 1.8, Vth is the threshold voltage here. I have applied here 1.8, for this one 1.8 minus Vth, and this is less than 1 point, sorry, this voltage, this potential V is less than 1.8 minus Vth. Three different conditions. For this case, Vds suppose this is, I have grounded this one. So Vds is equal to 1.8 volt, Ds is equal to 1.8 volt, this one, and Vgs is equal to 1.8 volt minus Vth. This one. The next one is Vds. What? Oh, sorry, I have it's wrong. Sorry. Yes. For this one, 1.8 minus Vth. This is Vds, and this side is 1.8 minus second condition. Third one is, this is V, this voltage, I have taken V. Now V and this side is 1.8 minus Vth. Now V is, it's not greater than, it is, for example, this is less than this one, 1.8 minus Vth. Okay. So in that case we can have, this is the condition. So this is equal to Vds now. Now this is the first case, second case, and the third case. Now we can apply maximum voltage here, that is equal to 1.8 volt at the gate, 1.8 volt. So to keep this one within triad region, the maximum potential what we can apply, that is less than 1.8 minus Vth. So that is the condition. No, actually this is, sorry, yes. It should be less than this one, this voltage VDS. So if we are maintaining this condition, then these switches will be in triode region. Now this is the curve. So if it is in deep triode region means that is very closer to that, and VDS is very less here. So in that case we can have very good switch. So to design switch, we have to always keep in mind that we should keep those MOS in triode region. Now, do you have any idea about Z transformation? Now let's see how the frequencies analysis is done here. Now this is one signal that I have applied here. And these are alternate pulses, phi 1, then phi 2, non overlapping pulse, then phi 1 again, then phi 2, then phi 1. Now if this signal, if we are writing this one as now this signal is equal to V start, this T is equal to, we are writing like this way, that O is for odd samples and E is for the even samples. So this is, I mean, this T by 2 is multiplied by N. Now if N is equal to some odd number, then for that case we are taking these samples, this one, then this one, then this one, first one, third one, fifth one for this case, and for this one, the second one, then fourth one, these samples. Now we can write like this way, that now for certain instant, now this was the V start T, it was that signal. Now T is the time period of that sampling pulse and T by 2 is the half of the time period. Now as these two pulses are non-overlapping pulse, at the same time they have equal time period, so we are taking samples like this way, that for that T by 2 multiplied by N, at that instant we can write those samples like this way, that n, it contains 1, 2, 3, 4, 5, all the samples for this one, and this is equal to, if we are taking the odd samples, then this is equal to n is equal to this one, 1 for 1, then third one, then fifth one, like this way. And for the even samples, second one, fourth one, like this way. For example, I have written like this way, that n multiplied by t by 2 is equal to v for the odd function n minus 1 into t by 2. Now this is equal to n is equal to 1, 3, 5, like this way. Now if we put n is equal to 1 here, then we will get the first sample, that is equal to 0th sample. Then for n is equal to 3, we are getting the first sample, sorry, the second sample, this one. Then n is equal to 5, we are getting this sample. And here for the even functions, for n is equal to 2, we are getting the 2 minus 1 means 1 for the first, that means the first sample, then this one, then this one, this sample. Now like this way you can write. Now this v star n t by 2, for this function we can write z transformation vz So this is the way how we represent the Z transformation. So this one, sorry, not this one, we can write this to, then I did one mistake, sorry. This is the way how we get the Z transformation. Now if this signal is equal to this signal plus this signal, so we can have Z transformation of V star Z is equal to V odd function of this one plus this one. Now this is a switch capacitor circuit blocks. Phi 1 and phi 2, two pulses are given here. At the input we have given one signal, Viz is equal to Vi for input, and O is that for odd signal, and E is for the even signal. So V suffix I, O, then Z plus Vi for the even function, Z, this one. Now the output we are getting, V out Z is equal to V, this is for the output, this suffix, and again for the odd function and the even function. So the transfer function is Z, we can write like VO Z plus Now this is a sample, this is a discrete sample architecture, one type of. Now how can we map this one with the continuous frequency response? Z is used for the discrete samples. For example, we have taken for the phi 1 pulse, for the phi 2 pulse, for these cases, and for continuous signal we use this one, this function h of s. S domain, do you have any idea about the S domain? Now for continuous signal we get the frequency response using this Laplace transformation, and for the sample data technique we get the frequency response using this Z domain. Now how to map these two things? Now S is equal to sigma plus I omega, and Z is equal to R e to the power j omega t. I hope so. Now to get the frequency response in continuous time signal, we make this sigma is equal to 0 and we put S is equal to j omega here in Hs and make it j omega, and here to get frequency response for discrete time signals we make R is equal to 1. So Z is equal to e to the power j omega t, and we put this one in H of Z. So e to the power j omega t. Now this omega, this is frequency of that input signal. This one, omega is the frequency of this signal, and this t is the time period of these pulses, small pulses. So we are considering that the frequency of these pulse, if pulse, is very greater than frequency of that signal. We are considering this thing. So now we can have a nice approximation. Z minus 1 by Z plus 1 let's take this expression. Now we are putting Z is equal to e to the power j omega t in this equation. So 2 by t e to the power j omega t by 2 e to the power j omega t by 2 minus 1 by so if we are dividing this one by 2 by, sorry I have, this is equal to, yes, minus j omega t by 2 equal to plus e to the power minus j omega t by 2. So these two will be cancelled, 2 by 2, this is equal to j, and this j will be multiplied by here. So this is equal to sin omega t by 2 by omega t by 2, 2j by t tan omega t by 2. Now as I have told just now that here the frequency of that pulse is much more greater than the frequency of that signal. So we can approximate this one, that omega t by 2. So we can write this one omega by this t means f of pulse twice pi, sorry not twice pi, this one pulse multiplied by 2. Now this is much more greater than this one, so we can consider that this is this is, I mean, this amount is very small. So for that we can approximate 2j by t into omega t by 2, like tan theta tends to theta, theta tends to 0. Now here we can cancel these two, and this is equal to j into omega, that is equal to s. So this is bilinear transformation, that s is equal to 2 by t z minus 1 by z plus 1. So what we do, first we take the signal, after that we break the signal into that even function and the odd function. This is the switch capacitor block, this one. So we are giving input here, after that we are getting output here this side. So we are giving this signal, after that we are breaking these signals into different samples. From the samples we are getting the z domain transformation, and from this z domain we are getting that this is the transfer function in z domain, and from this z domain we are applying this bilinear transformation, this one, and from here we are replacing the z by this one, like, I mean, we have that relation that s is equal to this one, so we can replace this z by the corresponding value of s in that transfer function. I have shown here in this transfer function. Okay. Now from here we can get the frequency response in continuous time domain. Now the higher will be the value of that frequency of the pulse, the better will be the accuracy for this case. Now coming back to the first circuit, now this is equivalent to resistance R. Now how to make different types of circuits using switch capacitor technique? We can have different amplifier, we can have different types of filters also. Now using an op amp, suppose we would like to design one inverting amplifier. So this is R1, this is R2, this is VI T and V out T. Now how to replace these resistors? Phi 1, C1 and Phi 1, C2. Is this clear? This one? Now this is one resistor and this is the another resistor. Now what will be that gain? V out by V in is equal to minus equal to R2 by R1. So it must be T by C2 by T by C1. You can cancel these T. and we can have V out by V in is equal to minus C1 by C2. The problem with this type of circuit is this. Now when phi 1 is on, so this will be charged. At the same time, we will have this output. Now during that period phi 2 is off, so these two switches are off. Now when phi 2 is on, that time, now this switch is off and this switch is off. So what will happen now? The amount of charge that was transferred in the previous phase, it will go like this way, this side and this side, and this is the virtual ground, and these two nodes are off. Now the problem of this type of circuit is that when phi 2 is on, phi 1 is off. Now this potential, the voltage of this node is floating now because this is off. Now we cannot define the voltage of this potential this node now. So that is the problem of this type of circuit. Now how to remove this problem? To remove this type of problem, we have another type of switch capacitor circuit techniques. That is, phi 1. Now we design the first circuit using this one, using this type of resistor, this type of circuit. Now this is one equivalent of, this circuit is equivalent to this circuit, but this can eliminate this type of problem. This is bilinear switch, this one. So to remove that type of problem, we can use this type of switch in those cases. So how can we draw the circuit now? But here we need more switch. So that is why to eliminate this one also, we have another very good solution using less number of switch. Phi 1 C. Now see, in this circuit, just we have replaced this circuit by this one. This one, the whole circuit, using this simple circuit, this one only. So what we are doing here, for the first one, when it is getting charge for the phi 1, then phi 2 is off. So during that period phi 1 is on. So this is at ground potential. So during that charging, we will have this one is equal to 0 volt, and when phi 2 is on, when it will be charged, that time phi 1 will be off. So this charge will be transferred using this path. So we will have V volt. So here in this case, we do not have any floating node for this case. Is it clear? This one. For this circuit, now is this circuit clear? This one, that when phi 2 is on, then phi 1 is off. So when phi 1 is off, so there is, I mean, this node is connected, I mean, this node is not connected to any other voltage. So this is floating, this voltage. Now what we are doing here, we are keeping this portion the same, this portion. Okay, we are changing the whole portion here using one switch and with that a parallel capacitor, this portion. Why? Because, and we are making this one as phi 1. Phi 2. Now when phi 1 is on, it will be charged. At the same time phi 2 is off. So this potential node voltage is equal to this node voltage. This is virtual ground. So this will be 0. V out is equal to 0 volt. And when phi 2 is equal to on, phi 2, so by that time this is charged with, suppose this is equal to V1, so it will be charged with V1. Now this is charged with V1 and phi 1 is off now. So it will take this path. Now is it clear now? Now we are getting voltage V for that case. So there is no floating node now for phi 1 and phi 2 both. So this type of circuit technique we use for the amplification, replacing those resistors by these capacitors. But we can use this is another technique also. This is bilinear switch, but as we need more switches here, so this is why we avoid this one. Suppose we need a summer, we would like to add 2 voltage. V is equal to 10 V1 minus 5 V2. For that, now we need, suppose we want to design one circuit that will give this expression, this one. Now we have got that for the switch capacitor amplifier, that voltage gain, suppose this is equal to C2 and this is equal to C1. Vi V out. So voltage gain V out by Vi is equal to C1 by C2. So suppose this is C, so you are maintaining the ratio only C by 10C, C by this one. This is 5C. Now what is happening? See here. Now this is phi 1. This is phi 1. This is phi 1. This one is phi 1 and this one is phi 1. Cross connection. Now when phi 1, then this will be charged at this path. Then phi 2, they are off. So this node will have V1 voltage, this node. Now phi 2 is on. When phi 2 is on, then this switch and this switch will be on. So this node will be connected to ground. So automatically this voltage will be shifted to this side. So this will be now positive. And if this is positive, this is negative. This is positive, this node is positive. Okay, I am trying to clarify this one. For the phi 1, it is getting charged like this way, this path. Is it clear? After that, when phi 2 will start, by that time this potential will be equal to V1. Clear? Now when phi 2 is on, then this node will be connected to ground. Is it clear? Phi 2, when phi 1 is on, phi 2 is off, the voltage of this one will be V1. And this side is equal to 0 because phi 1 is on, this side also, this switch, this is equal to 0. Now when phi 2 is equal to on, then this switch and this switch, these two switches are on. So that time what will happen? Now this switch will force this plate to be grounded. So the charge will be shifted to this side. It's not clear? Which direction? No, it's not like, for example, suppose you have positive voltage here, you have ground here. Now if you are making this node is equal to 0 and this is connected to another switch, so automatically you will have this voltage at this side. Okay, try with this one again. Now this was charged with V1 voltage. Now this switch is on. When this switch is on, then this positive charge is going to this side. Now when it is going to this side, obviously this switch is connected to this capacitor. So now this is negative, so this side is positive. So you are getting it at this side, you are getting 10 V1 for the first one. For the second one, what is happening now? Now these two parallel switches are on now for the phi 1. So these two are making this capacitor, and across the capacitor it's making voltage 0 when these two are on. Now phi 2 is on. Now phi 2 is on, both the phi 2 switches are on, so V2 voltage. Now this capacitor will be charged now using this path. So now when V2, so this side will be positive voltage, this side will be negative voltage, this side will be positive, this side will be negative. So now 10 V1 minus 5 V2. So you have to now design how to use these switches, because for the first one, see that I have taken like phi 1, then phi 1 here, then phi to this side and phi to this side, this one for the first one, and for the next one I have taken phi 2, then phi to same side, phi 1 and this is equal to phi 1. So using this we are coming to a different circuit, that for non-inverting circuit, for example, we have an integrator R C V1. Now this is inverting integrator, this one. The result will be a inverting voltage. So for this type of circuit, now this is the switch connection, that if this is inverting, then this is, if this is phi 2, then this is phi 2, this is phi 1, then this is phi 1. And C, this is Kc. If we would like to get again, G is equal to minus K. Clear? And for the non-inverting case, the switching connections are if this is equal to phi 2, now this will be phi 2, and if this is phi 1, then this will be phi 1. Now we can interchange also, that that means that if this is phi 1, then this will be phi 1, and if this is phi 2, this will be phi 2. So for the non-inverting case, the same switches are parallel, and for this is for the, I have written wrong thing. This is for the inverting. Okay, this is first one for the inverting, the next one for the non-inverting. As I have shown here also, that V1 is equal to, V1 is for that non-inverting. Non-inverting means you have got positive voltage here, okay, and V2 for the inverting case. So this is the switching condition. Now for the inverting, you will have same switch at the same side, and for the non-inverting, we'll have at cross connections. Now this is non-inverting inverting integrator, and this is non-inverting integrator, this one. Now for this inverting circuit, we have transfer function Hz is equal to minus k by 1 minus z to the power minus 1, and for this one equal to z into minus k into z inverse 1 minus z to the power minus 1. Using that z transformation, you will get these two functions. Now for example, it's another different circuit. This is a 3-stage op-amp circuit. First one is a damp integrator, next is an inverter, and third one is the integrator. Now how to design this circuit using switching capacitor technique? How to replace these resistors? Have you drawn this one? Can I change the slide? Here also I can do. Okay. Now see the first circuit. Now in this damped integrator, we have first this connection, this is the integrator, then this is the amplifier equivalent circuit, and the last one is also an amplifier. Now this is one inverter, the next is integrator. So these two things, we can combine these two things, and we can make this one that this is a inverting integrator and this is non-inverting amplifier. Okay, so if we are combining these two, then we can make this one as non-inverting integrator. So we are replacing this one, we are replacing these two by non-inverting situation. For example, if this is phi 2, then this is phi 2, this is phi 1, this is phi 1. Clear? This is K1 C, this is C. Clear? The first case, is it clear? Shall I repeat? Now coming back to the first stage, first we are taking the first portion, this is the integrator only. So to make this integrator, only this one, this resistor and the capacitor, we are taking this one, that this is integrator and this is inverting integrator. Okay, so what we are doing, we are making this one as phi 2, phi 2, phi 1, phi 1, K to C, C. Is it clear? This is for the, this is inverting integrator, this is non-inverting integrator. Okay, now this is a feedback. Now see this one, this is another feedback. Now coming back to this side. So how we are designing this circuit, now if this is coming to this side, so this is equal to a non-inverting, sorry, inverting amplifier, this resistance along with this resistance. So what we are doing here, see, now if this is phi 1, now how do we make non-inverting case? That switching should be, sorry, it's inverting, switching should be at the same side. If this is phi 2, this is phi 2, this is phi 1, then this will be phi 1. Now we are connecting one capacitor here, and we are making like this way, that this capacitor, see this one, now we are connecting this phi 1, I mean these two switches will be parallel, these two switches. So if phi 1 is, if this is connected to this capacitor, so we are making in such a way that this is phi 1 and this is phi 2. Now have a look on this circuit. Now for this one, for this capacitor, this is the capacitor. Now this is phi 1, this is grounded phi 1. Now this is equal to phi 2, and here this side, this is phi 1 is grounded, this is phi 1 grounded, and this is phi 2. Actually we are minimizing the switch. We can design also, I mean having those direct blocks, I mean this is one resistor, another resistor, directly just copying this type of things, but we cannot use so many switches. This is why we are minimizing the switches, and that's why we are drawing like this way. So is it clear, this one, this portion? So like this way, so this is done, this one is done, third one is done. Now the fourth one. Now if this is phi 1, the last one, see last one. Now last one, from this last one, this feedback is coming from the last node. This is another resistor. Now this resistor along with this resistor, these two resistors. They are making another inverting. They are making another inverting amplifier. This one. So what we are doing here. So this is also another inverting case. So you are taking output from this side. This side. So this is the capacitor now. Now again see. Now if this is phi 1, this capacitor. So here same thing. This is phi 1. Sorry. I mean, this is the feedback capacitor. Now this is also inverting case. So if phi 1 is parallel to this capacitor, so from this capacitor we are applying phi 1 here. Similar thing. What I am doing here? Similar thing. And phi 2 is here. So we are adding phi 2 here. Clear? Huh? Now let's take a fresh design of this circuit. Is it clear? Now notice one thing, that if you are making this switch phi 1 instead of phi 2, then you have to change all the switches according to that. And till now this portion is fine.